Welcome to our discussion on the derivative as a function. We've already seen how we can describe the derivative as the slope of a tangent line to a graph, right, or to a function at a particular point. And we've seen this nice description, this nice function that defines the derivative at a point A as the limit as h approaches 0 of f of a plus h minus f of a all over h. Well, if you just did a straight substitution and swapped out a for x, you can see these two things are exactly identical, only now instead of the letter a, we're using the letter x. You've already figured out how to find the generic form of a tangent line rather than just finding the slope at a particular point. You've been able to find the slope of all tangent lines, and you get that answer, as an equation in terms of a. Well, now you're just going to get that equation in terms of x and realize that, well, because it's in terms of x, it's a function itself. So ta-da, that's it. All we're doing now is realizing that this slope of a tangent line that we can list as an equation, we can now list as an equation in terms of x, and because of that, we have a function. So the derivative is a function, and then the derivative of a derivative is a function, and so on and so forth. As long as we can keep taking derivatives, those are functions. Okay, so given any number x for which this limit exists, we can assign to x the number f prime of x. So we can regard f prime as a new function. We can call it the derivative of f, and we can define it by this equation. We know that the value of f prime at x can be interpreted geometrically as the slope of the tangent line to the graph at that point. And thus the function f prime is called the derivative of f because it's been derived from f by the limiting operation in this definition. The domain of f prime is just going to be the set of all x's where f prime exists, where it's defined. And that may actually be smaller than the domain of the function f that it comes from. So just like any other function, you kind of have to treat it individually and reassess its domain and range on its own merits. Here's a graph of just a typical old function. We'll call it y equals f of x. We can use this to sketch the graph of the derivative function, because if you started with some tangent lines, and you'll have to excuse my poor drawing skills, but here's, see what I mean? Horrible. Let's try that again. Here's one tangent line, right? Here's a tangent line, and then they go this way, right? Kind of steeper, and then they level off, and then they start coming down. Right down here, they're at 0. And so you can start graphing those slopes, because remember, the function f prime is just a combination of those slopes. Everywhere the slope was 0, then that function is going to cross the x-axis. Everywhere that you have these positive slopes, you have positive numbers, right? These are all going to be above, and then it's going to come back down to 0. So it's got to go up, come back down. Here's 0. These are now negative slopes, and then it's got to come back up and hit here, and then those are positive slopes. They keep getting bigger and bigger, right? In this direction, these are all negative, right? They're getting more and more negative. And so this is what your graph ends up looking like roughly. Now that's just from eyeballing it. If we wanted to actually be better, right, we could calculate a bunch of slopes, we could plot all those points, and we would get something that looks more like this. Now remember, this is what mine looked like. Just look at the overall shape, right? It gets bigger to the right, gets smaller to the left. It crosses the x-axis in 3 points and kind of has, one hump and one valley. Well, look at that. Smaller to the left, bigger to the right, crosses at 3 points, has one hump and one valley. So you can always get the overall shape of it, but who's going to know that this part of the function actually had kind of this kink in it, right? And whereas this one was just more kind of standard parabola looking, right? You can't do that by hand, you can't do that by eye, you have to actually let technology do that for you. Alright, so if we wanted to do this by hand, what we would have to do, the easiest thing, the best thing to do is to start with the zeros. So you start by finding A, B, and C, the three places where you saw the derivative was equal to 0, you know that's where it crosses the line. And then you work from there. You figure out, okay, in between those two values, were the slopes positive or were they negative, right? And that tells you if it's a bump or a valley, and then you just kind of connect the dots. All right, the derivative is a function. Another example. When we let x be very close to 0, we know that the square root of x can also get close to 0. So the derivative of f of x, which equals 1 over 2 root x, is very large, and this corresponds to the steep tangent lines near 0, 0. The graph on the left is the graph of the function, the square root of x, from 0 and above, right? Because it's not defined for things below 0. And if you remember, that looks like a parabola on its side. And so it's very steep at the beginning and then starts to kind of level off. Well, if you were to graph those slopes, you would have an undefined slope at 0, right? Because it would basically be vertical. And then it starts to peel over and it's positive, but it's less and less positive, getting closer and closer to 0, and that's how you get the red curve, which is the derivative of the function, which happens to be 1 over 2 root x. You don't know how to make that yet, right? You don't know how to get that derivative yet, but we will figure out later that that is in fact the derivative. Okay, if we use the traditional notation of y equals f of x to indicate that the independent variable is x and the dependent variable is y, then we can get some common alternative notations for the derivative as well. F prime of x can also be listed as just y prime. We can also talk about it as change in y over change in x, which we now list as dy over dx. Instead of deltas, we just do dy. But y is the same thing as f, so we can call it df dx. We also tend to bring the dp pieces out and then have ddx of this function f, or just a capital D of f of x, or a capital D with a little x to let you know that it's a derivative with respect to x of f of x. These are all acceptable different ways of writing a derivative. The kind of the three most common ways. This way is probably the most common. This way shows up a bit. And then anything with the d's, dy dx is probably second most common to f prime. df dx you don't see that much, but you do see ddx of some stuff, right? So those are kind of the four most common ones. Okay, the symbol dy dx should not be thought of as a ratio, at least not now. Later on, maybe. But you're not dividing dy by dx. It's one of the reasons why I like the f prime notation, because it doesn't lead to that error, and then I like this one because you kind of think of it as ddx of something, right? It still can lead to some misconceptions thinking that you're taking something times, right? Because this kind of feels like multiplication, but you're not. You're applying a ddx application, right? So you're applying kind of a function to a function, because that's really what you're doing when you're taking the derivative. It's almost like you're applying a function to it or an operation to it. All right, these two notations are almost never used. I never see these. They're in the book, so be aware that if you see it, that it just means the same darn stuff, but I wouldn't bother with them. We do, however, have one other definition to worry about. We know a function f is differentiable at some point a if the derivative at that point exists. it's differentiable on an open interval, meaning from the points A to B, or from A out to infinity or negative infinity to A, or even if we want the open interval to be all numbers, negative infinity to infinity, if it is differentiable at every number on that interval. So duh, right? So we're just basically defining what it means to be differentiable. It just means that the derivative exists at that point. And if it's differentiable on an interval, then that means we can calculate the derivative at every point in that interval. Okay, with that in mind, where is the function f of x equals the absolute value of x differentiable? Well, we know that if x is positive, right, if x is greater than 0, then the absolute value of x just equals x. You put in positive 5, the absolute value gives you 5 outright. You put in positive a half, you still get a half. You put in positive 100, you still get 100. Okay. So with that, we know that we can choose h to be small enough such that x plus h is also greater than 0, and therefore x plus h absolute value is also equal to just x plus h. Therefore, anytime x is greater than 0 and we want to try and find the derivative, we take the limit as h approaches 0 of f of x plus h minus f of x all over h, which is just the absolute value of x plus h, right, minus absolute value of x. But because x is greater than 0, those things are just equal to their normal counterparts, meaning you can just drop those absolute value signs and everything's still the same, and you get x plus h minus x, right, all over h. The x's cancel, you get h over h, the h's cancel, and you get 1. And so the derivative is just equal to 1 whenever x is greater than 0. And therefore we have f is differentiable for all x greater than 0 because we just found that the limit existed, right, for everything. It was always 1. It was just a constant. Similarly, we can do the same argument for x less than 0. We know that the absolute value now gives us the opposite number, right? You put in negative 3, you get a 3, which is the opposite, right? It's the negative of what we started with. It's negative 3. And similarly, the x plus h is also going to be less than 0, and so on. We can do those substitutions, and now when you start with the original functions here, right, and you want to take them out of the absolute values, you now just have the opposite of them, and then the opposite of this. Distribute your minus signs, distribute this, combine like terms, and you're left with negative h over h, or negative 1. And you see that whenever x is less than 0, the derivative is equal to negative 1. All right, what about if x equals 0? Well, if x equals 0, we can just plug in and figure out what is the derivative at 0, and by plugging it in, we just get h over h, right? 0 plus h is just h, minus 0, those go away. You get h over h. You let h go to 0. Well, h over h still becomes 1, and so you get that 1 again. But that's really only if it exists. So you got to check and make sure the limit actually exists at 0. When you look at the left-hand limit, you get that you have an answer of 1. But when you look at the right-hand limit, you get an answer of negative 1. And if the left-hand limit and the right-hand limit are not the same, then we know the limit does not exist. And if the limit doesn't exist, the derivative doesn't exist, and therefore it's not differentiable at 0. Which is pretty obvious if you look at the graph, right? Because how can you put a tangent line on that point? Where does it go? Can you imagine that if you put a ruler against a square edge like that, couldn't you rotate that ruler through basically all 90 degrees and it would still only be touching in one spot? And a true tangent line touches the graph in one spot, but it can't move, right? It can't have different slopes at that one point. And this brings us to the idea of continuity and differentiability. If f is differentiable at a, then f is continuous at a. So if the derivative exists, then f is continuous at that point. But we just saw from the previous example that the function wasn't differentiable at 0, even though the function was continuous at 0, which tells us that the converse of this theorem is false. Meaning, just because a function is continuous does not mean it's differentiable. It doesn't go both directions. If it's differentiable, then it has to be continuous. But if it's continuous, does not make it differentiable, as we saw from this example. And in fact, in general, anytime you have a graph that has a sharp corner or a kink to it, right? It's not a smooth curve, but it's got some sort of jolting corner, then you will not have a derivative at that point because you will not have a tangent line at that point. And from theorem 4, we get another way for a function to not have a derivative. It says that if f is not continuous at a, then f is not differentiable at a. So at any discontinuity, for instance, if you have a jump discontinuity or if you have a vertical asymptote, right? So you have a discontinuity that way, then the derivative doesn't exist. Here are some graphs, right? Vertical tangent line where we have that weird looking graph and a vertical tangent line from the one on the other. Both of those, the derivative doesn't exist at that point. And the reason why the derivative doesn't exist is because the derivative is the slope of the tangent line, and the slope of the tangent line is undefined, right? It's an undefined slope for a vertical line. Here are three possibilities of problems where f would not be differentiable at a. The first one, you've got that sharp corner, that kind of kink in the graph. The second one, you've got a discontinuity. And the third one, you have a vertical tangent line. So those are the three major ways that you can have a function that won't be differentiable at a certain point. But you can see in all three of those examples, it would be differentiable everywhere else. So if a function is a differentiable function, meaning you can take its derivative, then its derivative is also a function. As we've seen, we list it as a function in terms of x. And therefore, the derivative function might also have a derivative of its own, right? Because you're just taking a derivative of a function like we did when we originally got the first derivative, and then we just get f double prime for the second derivative. And that's what we call it when we have this symbol here. This is just called f double prime. And that's the second derivative. Again, it's the derivative with respect to x of the derivative of y with respect to x, which we already had, and therefore we get d squared over dx squared, right? Do you see how there's two d's and two x's? And that's where this terminology or symbology comes from. Let's look at an example. Start with the simple function x cubed minus x. We want to find and interpret the second derivative. Well, the first derivative of x cubed minus x is actually 3x squared minus 1. Now, you don't know the tricks, or maybe you already do, but you'll figure out how to find that later. So just take it on faith. That is, in fact, the first derivative. Now we can take the derivative of that function using our same limit definition. So we're just taking the derivative of 3x squared minus 1. So we're taking x plus h of that function minusing f of x, right? X plus h just means x plus h squared times 3 minus 1, and then minusing the original function. You're going to need to FOIL that out, combine like terms, cancel things that are the same, right? You've got a 3x squared, a minus 3x squared, those go away. You've got a minus 1, a plus 1, those go away. You're left with just 6xh plus 3h squared all over h, right? So after everything cancels, you're just left with those two pieces over h. The h's cancel. You're left with this. You take the limit as h goes to 0, which kills off that piece, right? Because 3 times 0. And you're finally left with just 6x. And in fact, if you graph all of them on the same graph, you can see the blue line is the original function. The red line is the first derivative. The green line is the third derivative. Sorry, the second derivative. First derivative, second derivative. The third derivative would just be 6, and then you would just have a horizontal line at a height of 6. Okay, We can interpret f double prime of x, the second derivative, as the slope of the f prime function, right? It's just like before. The derivative is the slope of the tangent line. So the second derivative is just the slope of the curve, right? The slope of the first derivative, which basically tells us that's how fast the first derivative is changing, right? It's a rate of change of change. It's a rate of change of how fast the derivative is changing. In general, we can interpret a second derivative as a rate of change of a rate of change. And the most familiar example of this is acceleration. It's how fast your velocity is changing. The instantaneous rate of change of velocity with respect to time is going to be called acceleration, and that's going to end up being the first derivative of velocity. And of course, velocity was the first derivative of position, so acceleration just ends up being the second derivative of position. The third derivative is the derivative of the second derivative, and it's basically the rate of change of your acceleration. Right? It's how fast acceleration is changing. And it's just f with three of them, f triple prime. And then, of course, if we go to four of them, from 4 on, we start to just use letters. So we use f with a little 4 in parentheses, and then f with a little 5 in parentheses for the fifth derivative, and so on and so forth. When we want to try and interpret what the heck that third derivative is, remember it's the rate of change of acceleration, and in physics that's called a jerk. I know it's silly, but that's what it's called. And if you think about it, if your acceleration changed abruptly, the car would jerk, and so it makes sense to call it that. Okay, and that's really all that we have to worry about with higher derivatives for now, is that the first derivative of position becomes velocity, the second one becomes acceleration, the third one we call a jerk, right? It's the change in acceleration.